You are drowning in an ocean of invisible particles. They fill up every corner of the room you're in right now, every hemisphere of the Earth, every orbit in the solar system, every spiral arm of the Milky Way. Take a deep breath. Uncountable trillions of these particles stream through your lungs. Reach out your hand. They are piercing your skin as we speak. Look across the room. If you could see these particles, everything, and I mean everything, would be completely obscured from view, lost in a thick haze of this frenzied, unstoppable flood. This is our picture of dark matter, the invisible form of matter that astronomers believe makes up the vast majority of the mass of almost every single galaxy. What we see in the visible universe, aglow with billions of stars, elegant nebulas, and grand galaxies, is but a mere fraction of the true structures of the large-scale cosmos. The dark matter subsumes the ordinary matter, and yet for a few indirect observational clues, it eludes our grasp. Despite the fact that countless particles are streaming through us right now, we can't catch one for ourselves. We are at the edge of a revolution. We hypothesize the existence of dark matter to explain a wide variety of astronomical observations. But if we don't come up with something soon, we'll be forced to reconsider the basic foundations of modern cosmology. Thankfully, I have good news for you. We may just have one last trick up our sleeves, a particle predicted to exist in the arcane corners of high-energy physics that may yet solve this dark matter mystery. But what is dark matter, and why do we believe it exists in the first place? I know you may encounter on social media or YouTube some intense skeptics of the dark matter hypothesis, but there's a reason that the vast majority of physicists, astronomers, and cosmologists believe that we're on the right track. That said, all knowledge in science is provisional, and while dark matter is the best idea we have right now, it doesn't mean that we have to hold on to it forever if it doesn't pan out. And I'll be honest with you.
You're a real straight shooter.
Things are starting to look a little curious. So let's see where the evidence has taken us, why we believe what we believe, and where future experiments and theoretical concepts might lead us. I'm Paul Sutter, a cosmologist, author, and NASA advisor, and this is Near Futures. In the 1970s, Vera Rubin didn't set out to upend modern cosmology. She was just always curious about the heavens. It started with building a homemade telescope out of cardboard and glass, and it progressed with her becoming the only astronomy undergraduate student at Vassar College, graduating in 1948. She was qualified enough to get into Princeton, except for the fact that she was a woman, and so they wouldn't let her in.
How can I hate women? My mum's one. Yeah.
Despite years of discouragement and harassment, she made a name for herself in cosmology, joining the first generation of scientists to piece together the large-scale structure of the universe. But it was her observations of the Andromeda galaxy that changed everything. She became interested in studying the motions of stars and gas clouds within that galaxy. Nobody expected something radical to come out of these measurements, but it was worth doing anyway. It's a classic case of science by sheer exploration. Go out and measure something and see if something interesting comes up. And something interesting came up. She was especially interested in the rotation rates within the galaxy as a function of distance from the center. The rotation rate at a given distance should neatly line up with the amount of matter contained within that distance, and how great that distance is. This is Kepler's laws, and later Newton's laws, and then Einstein's general relativity at work. The orbital speed is related to the amount of matter within the orbit, just like the Earth's orbital speed is dictated by the mass of the Sun and our distance from the Sun. It's relatively easy to measure the amount of matter within a given orbit, especially with something like the Andromeda galaxy that shows a good fraction of its face to us. We just measure the brightness, which is proportional to the number of stars, gas clouds, and other generally glowy things inhabiting a galaxy. And by just looking at a picture of a galaxy, you can tell that most of the stuff is concentrated in the center, and then it just sort of tapers off from there. So we expect that orbital speed should be really, really high near the center, and then just sort of taper off from there. At the very edge of a galaxy, you are very far away from all the stuff, so you should have a slow and lazy orbital speed. Except, as Rubin discovered, you don't. The very edges of the Andromeda Galaxy were spinning almost as quickly as the middle parts, and even the center. In fact, the rotation rate across the galaxy was almost constant. And it wasn't just some galactic fluke of Andromeda. Rubin went on to measure dozens of galaxies and consistently got the same result. It appeared that the material in every galaxy was rotating far too quickly given the amount of matter that we can see. This is the essential observational reality of the whole dark matter idea, a reality that crops up again and again. At large scales, nothing ever seems to line up. There's an extra source of gravity, some extra glue that's holding galaxies together. By all rights, Rubin should have won the Nobel Prize, and by now, just about everybody agrees that if we were talking about a Victor Rubin, the prize would have been his. But hey, in 2025, Vera will be featured on a special edition of the US Quarter, which I guess is going to have to be the consolation prize.
Take this quarter.
Anyway, it's not just galaxies. All the way back in the 1930s, Swiss-American astronomer Fritz Zwicky, who really knew how to rock a bolo tie, and for that, I applaud him, was studying the Coma Cluster, a nearby cluster containing over 1,000 individual galaxies. In Zwicky's case, he found that the galaxies themselves were buzzing around far too quickly for the mass that he could observe. The cluster should have simply dissolved eons ago, with the individual galaxies just flying away from each other. But there the Coma Cluster was, just serenely sitting there like there wasn't a problem at all. For his work, Zwicky earned himself naming rights. He suspected, but could not prove, that the Coma Cluster was bound together by a hidden source of matter, a Dunkel Materie in German, dark matter in English. Despite the mystery, he and the rest of the astronomical community would put the problem down for later generations to solve. By now, we are further removed from Rubin's discovery than she was from Zwicky's, which means that we've had a lot of time to think about what dark matter could be, and a lot of time to go looking for it in the universe. And to be frank, we see it everywhere. Well, I mean, we can't see it because it's invisible, but we see evidence for it every time we make any sort of observation of the large-scale universe. The evidence that something funky is going on with the universe is substantial, to say the least. I could devote an entire series of episodes on the evidence for dark matter alone, and don't tempt me. But let me give you a quick rundown. By now, we've measured tens, maybe even hundreds of thousands of rotation curves of every kind of galaxy. They all rotate with speeds far too great to explain with the matter that we can observe. We've measured thousands of galaxy clusters with the same result. There's even funkiness in the cosmic microwave background. This is the radiation left over from when the universe became a neutral gas when it was only 380,000 years old. This radiation completely covers the sky and is responsible for over 99.999 and a few more nines% of all the radiation currently in the universe. It's almost perfectly uniform, with the exact same brightness and temperature. But it does have tiny 1 part in a million differences known as anisotropies. Those differences tell us what the universe was up to all those billions of years ago. We can create models of that early universe, plugging in various kinds of ingredients and forces and physics and whatnot, and compare that to what we see. No matter how you massage the math, no matter what exotic chicanery you concoct, you can't replicate the signal of the cosmic microwave background without including some additional source of hidden matter. You just can't. So why do we think that dark matter is matter? How do we know we aren't just getting gravity wrong or some other aspect of physics? Yes, dark matter has a cool name and so has great marketing behind it, but that doesn't make it real. How do we know that we're even on the right track? As a kid, you ever play that game, Guess Who? If you haven't, it's actually kind of fun. You have two players, each with a board in front of them. On the board are a bunch of flip cards with different characters. You have to guess your opponent's secret identity through a process of elimination. You ask if they're a kid or an adult or a boy or a girl, or if they're wearing glasses or they're bald. If you ask the right questions and eliminate the correct possibilities, you're left with only one remaining option: your opponent's secret identity. Whenever I think about our search for dark matter, I can't help but think about that game. We have something going on in the universe. One kind of observation, measuring the amount of hot, glowy, visible matter, isn't lining up with all the other kinds of observations, ones that tell us about the total amount of matter in the universe. To explain this discrepancy, we have an exceedingly wide variety of options. Theorists are no slouches, and as soon as the evidence for something new and exciting appeared in our observations, they started cooking up ideas. Ideas like Patreon. That's patreon.com/pmsutter, where you get to support this show and keep it going. I truly appreciate all of your contributions. That's patreon.com/pmsutter. You can also use the link in the episode description below. There are a dizzying array of models, hypotheses, wild guesses, and brilliant but wrong insights. Beginning with Vera Rubin's groundbreaking measurement, we've been hard at work playing a game of galactic Guess Who. But any idea of what's causing the discrepancies in the observations has a huge challenge in front of it. It has to explain all observations, pass all tests at all scales at all times, from galaxy rotation curves to the cosmic microwave background and more. For example, one might reasonably assume that maybe the dark matter is just dim matter, like black holes, something that's not easy to see. It's easy enough to fill up a galaxy with extra black holes to account for rotation curves. But how do you get those black holes in the spaces between the galaxies to account for cluster observations? Or populate the early universe with enough black holes to account for the cosmic microwave background? The cosmos isn't all that great at forming black holes. First you need stars to live and die to make some, so you can't account for all the dark matter just through black holes alone. An abundance of black holes may explain one observation, but not all. Or maybe it's neutrinos. Those ghostly little particles that hardly ever interact with normal matter. At first glance, they're an ideal dark matter candidate. There's a lot of them. They have a little bit of mass. They are really, really hard to see. But in this game of Guess Who, we have to eliminate them. That's because they're hot. In cosmology terms, they travel at nearly the speed of light. This means that they're not good for building structures like galaxies. Neutrinos make them too smoothed out. If we were to fill the universe with enough neutrinos to explain the dark matter, then we can't get galaxies to form. They would just be spread out blobs of gas. An abundance of neutrinos may explain one observation, but not all. What about alternative forms of gravity? Perhaps the most famous of these is MOND, for modified Newtonian dynamics. Essentially, it's a fix to Newton's gravity carefully crafted to explain galaxy rotation curves. It just says that at large scales, our usual understanding of mass, force, and acceleration is a little bit off. Yeah, it's not the most rigorous thing in the world, but it's a good start. The trouble with MOND and all of its related theories is while that they can be tuned for one particular scenario, they have trouble extending to other scales. For example, you might be able to nail galaxy rotation curves, but then you have difficulty getting the details of clusters right, especially interacting ones like the famous bullet cluster. This is a composite image showing the components of a merger between two galaxy clusters. You can see the individual member galaxies, which have largely sailed past each other unharmed because there's a lot of space in a cluster. You can see the hot gas in the middle, which got all tangled up and shocked. And then you can see with gravitational lensing where most of the matter is, and it's not in either place. Simultaneously explaining images like these, along with galaxy rotation curves, along with the cosmic microwave background, is a task that no theory of modified gravity has accomplished. It doesn't mean that we're getting gravity 100% right, but to date, nobody's been able to figure out a compelling alternative that explains all observations. Even if these theories are correct, or at least on the road to being correct, the fact that they always come up short in one direction or another means that dark matter is unavoidable. You simply can't get rid of it. After half a century of guess who, we're left with very few possibilities. Modifying gravity isn't cutting it. An abundance of normal but otherwise dim or invisible matter isn't cutting it. The only hypothesis remaining is that dark matter really is a new kind of matter, some mysterious particle currently unknown to physics. The dark matter has to have a limited set of properties to match all known observations. It has to rarely, if ever, interact with light. It has to rarely, if ever, interact with normal matter. It might be able to interact with itself to some degree depending on the model. It has to be cold, which means that it has to move slowly compared to the speed of light. And it needs to be made in abundance in the extremely early universe so that it can participate in all of these cosmic shenanigans from the get-go. For decades, cosmologists were sure they were on the right track. They even had a name for their prime candidate, the WIMP, the weakly interacting massive particle. And so they set up detectors and specialized observatories around the globe to get that definitive proof that they were looking for. And that's when everything started going wrong. What if I told you that while you can't see dark matter, maybe you can hear it? I know, it sounds crazy, and it is crazy, but it's crazy enough that it just might work. It's a real-life experiment called the Cryogenic Rare Event Search with Superconducting Thermometers, or CREST. That's a double S, in case you didn't catch that. Look, it's not the greatest of acronyms, but we're going to just go with it. The experiment is buried deep under the Gran Sasso mountain in central Italy, which, by the way, Gran Sasso is Italian for Great Rock, in case you need some bonus trivia on your next date night. And it consists of a giant crystal of calcium tungstate, also known as scheelite. The crystal is cooled all the way down to just a few millikelvin, right on the edge of its superconducting state. The idea is that if a dark matter particle happens to intersect with the detector, it will cause the crystal to vibrate. I mean, the energy has to go somewhere after all, which will mess up the superconducting state and produce a detection. CREST has been operating for years and has yet to make a confirmed detection of a dark matter particle. But in science, an experiment is only a failure if you don't learn something. And we've definitely learned about dark matter with the CREST experiment. Specifically, we've learned what dark matter isn't. In published papers about dark matter detection experiments, you'll often find charts and graphs that look like this. Remember that we don't know the identity of the dark matter particle. We have some guesses based on various theories and concepts, but at the end of the day, we don't know the precise properties of that particle. Specifically, we don't know its mass or how easily/rarely it interacts with normal matter. We have some limits from our observations of the wider universe, and we've been able to eliminate a lot of possibilities like neutrinos. But after that, it's fair game. That means we have two jobs. On one hand, we need to come up with reasonable and well-motivated candidates, which involves a lot of creative brainstorming, theorizing, and guesswork. And on the other hand, we need to come up with experiments that can rule out specific candidates, or, failing that, put some more precise limits down on what kinds of properties the dark matter can have. That's how we end up with graphs like that, which are showing how that particular experiment ruled out certain mass ranges and interaction strengths of the dark matter. By simply running the experiment and not seeing anything after a while, you can confidently say which properties of dark matter are excluded. You can say that the dark matter cannot be this particular mass with this particular interaction strength. And then you do it again.
Again.
And again.
Again.
And again.
Again.
And of course you don't run just one experiment. Remember, the dark matter could have a wide variety of masses and interaction strengths, and no single experiment is able to cover the entire range. The possible mass of the dark matter particle can span a range of over 50 orders of magnitude. Because this is a particle, we need to use the language of particle physics, which means we express mass in terms of electron volts, or EV. On the large end, an individual dark matter particle might weigh 10 to the 24 to 10 to the 30 electron volts, which is somewhere between the mass of a bacterium and a small insect. We generally don't think dark matter particles can get much bigger than that, because anything with the mass of, say, a planet or a star would have shown up in gravitational lensing observations by now. On the other end of the spectrum, we can have ultralight dark matter particles going all the way down to 10 to the negative 21 electron volts, which opens up some really fun opportunities that I'll talk about in a little bit. But for decades, our prime dark matter candidate was the WIMP, that weakly interacting massive particle, which we thought had a mass range of a few billion or trillion electron volts, which is in the similar mass range of known heavy particles like the W and Z bosons and the top quark. So big, but not too big. We liked the WIMP because various theoretical extensions to the standard model of particle physics predicted the existence of a particle in that mass range and with the right properties, that is, mostly invisible. I will never stop saying this. WIMPs aren't the greatest idea in all of physics, and the whole dark matter hypothesis is all built on circumstantial evidence.
All circumstantial.
But of all the options we've got, it's the least bad one we had. It's the simplest explanation for the greatest amount of observations. It's the expression of this concept that we use a lot in physics, which is parsimony. We treat theoretical ideas like funding for graduate students. How do we get the most work for the least amount of effort? Or how do we get the most amount of explanatory power out of the fewest possible assumptions? The dark matter hypothesis has its shortcomings and certainly isn't able to explain every single observation. And WIMPs are just a hair above just straight up make-believe fairy tale particles. But any other hypothesis both has more assumptions, as more moving parts, and less explanatory power. It matches fewer observations. So, WIMPs it is. Until it isn't. That's because we can make all the arguments we want all day long about parsimony and observations and alternatives, but in science, nature is the ultimate arbiter of which ideas stay and which go. We need direct, hard, experimental verification if we want to go along with the dark matter story, which is exactly why we built experiments like CREST, to go hunting for WIMPs, collect a few Nobel Prizes, and move on to other exciting unsolved cosmological puzzles. We have run dozens of direct detection experiments around the globe hunting for WIMPs, dark matter particles in this particular mass range. And they're not all the same kind of experiments. There are also the scintillators, which use a giant vat of liquefied noble gas like several tons of xenon. They wait for a dark matter particle to strike the xenon and cause it to scintillate, which is a fancy science word for sparkle. We see the sparkle, we detect dark matter. WIMPs aren't alone. They're just one example of a broader class of dark matter candidates with delightful names like cue balls, WIMPzillas, and sterile neutrinos. We've tuned our different experiments to capture different mass ranges or interaction strengths to cover as much as that wide dark matter spectrum as possible. We've even tried to manufacture various kinds of dark matter in our particle collider experiments, and we found nothing. So where do we take it from here? We haven't learned nothing. After decades of searches, we're narrowing down the range of what dark matter can and cannot be. We strongly suspect that we're getting our theory of gravity right at galactic scales. We also strongly suspect that the dark matter is not some abundance of known particles like the neutrino. We also strongly suspect it's not something like black holes, although there are some possibilities there that I will tackle in a future episode, feel free to ask. We strongly believe, based on the weight of the accumulated evidence, that dark matter is a particle. But that same evidence is leading us to the conclusion that our prime candidate, a weakly interacting massive particle, is not it. It's not completely ruled out, but as the years go by without a solid detection, it makes us seriously doubt our assumptions, which is a good thing. This is how science operates. Most ideas in science are wrong because we're constantly learning new things. And we only get to learn new things by trying out as many ideas as possible and seeing what sticks. Wimps aren't seeming to stick, so it's time to think of something else. Which brings me to axions. The gist is that maybe dark matter isn't some heavy particle, comparable in mass to a quark or a weak boson, or even an electron, or even a neutrino. Maybe dark matter is really, really strange. Nature has no obligation to make sense, after all. Maybe dark matter is orders of magnitude lighter than the lightest known particles. There's precedent here, at least some vague theoretical motivation for a particle like this. Back in the funky 70s, around the time that Vera Rubin was observing rotation rates in galaxies, some theorists noticed that there was a strange issue with quantum chromodynamics, our model of the strong nuclear force. All experiments showed that the strong force obeys some special symmetries in nature, and yet the theory itself doesn't explicitly state that. To make the fix, you have to introduce some unnatural hand tuning, which is never a fun thing to do from a particle physics viewpoint. One way to solve this is to introduce a new kind of particle, which was named the Axion after a brand of laundry detergent. Get it? It cleans up messes. Now, the axion is interesting because it's A, a new particle, and B, could be made in abundance in the early universe, and C, doesn't interact with other particles all that often. Hey, that's the dark matter. Now, in the 80s and 90s, WIMPs became more popular as a dark matter candidate, but now that they are looking a little sketchy, we've started rummaging around in the attic looking for any discarded or overlooked ideas to see if something interesting pops up. And so now there's a lot of interest in axions. I'm going to be honest, they're also not the greatest idea in the world, but they're interesting enough to be worth pursuing. Axions themselves are just one example of a broader class of ultralight dark matter, which includes other candidates with delightful names like the ultralight scalar field and the dark photon, and they would be wild. One of the most fun things about axions and their relatives is that they are so incredibly light that their inherent wave nature comes out. All particles aren't really particles. They're mixtures of both waves and particles, something we know about from quantum mechanics. But the more massive a particle is, the more its wave nature is suppressed. Axions are light enough that we shouldn't think of them as trillions of microscopic bullets buzzing around the galaxies. Instead, we should think of them as an ocean, a sea of dark matter with the galaxies as lit up buoys on the surface. This ocean of dark matter even has waves, pockets of higher dark matter density and regions of low density. One way that we could access this dark ocean is through the possibility of axions converting directly into photons in regions of extremely strong magnetic fields. This conversion is incredibly rare, otherwise we would have noticed by now, but it gives us a potential window into the axion world. Searches for axions are just getting started, and they've already produced some limits on what the axion could be. There is no confirmed detection yet, but we've only begun to pivot in this direction. We're even tuning existing dark matter searches to see if they can sniff out an axion here and there. We don't have any slam dunk, case closed explanations for the dark matter mystery, and some of our best ideas haven't panned out. But the story of dark matter is just getting started. The universe is obviously trying to tell us something. The observational evidence is strong and clear that something is going on in the wider cosmos. Dark matter might be axions, or it might be something more exotic, or it might be something we haven't even begun to think of yet. Facing this challenge will require patience, persistence, and most importantly, creativity. So what do you think? Are axions worth pursuing as an idea, or are we totally off the rails? What next steps should we take in our hunt for dark matter? Let me know what you think in the comments, and we'll see what the future will bring.